This presentation will encompass 4 parts. The first phase is the introduction of the KNX Secure specifications, as they were published in 2017. The second part will be a presentation of the new features that are being worked on. That's the main part of this presentation. The final part will be an outlook on the new things that are being discussed right now. Let's firstly have a look at KNX Data Security. KNX Data Security provides the following security features. Data integrity. The message is protected by a message authentication code, a signature at the end of the frame. So, the receiver can verify that this message has not been manipulated. Confidentiality. The service and the payload can be encrypted, so eavesdropping is not possible. ETS always uses both authentication as well as confidentiality. Freshness. Freshness means protection against replay attacks. Every sender keeps an own sequence number for sending, which it increments with every message it sends out. This is stored by the receivers, and the next messages will by the receiver be compared with it, so it is not possible to replay the same message to the same receiver. KNX Data Security supports the following configuration modes: System Broadcast, Broadcast, Unicast, and Group Communication. Configuration is done secure by an out-of-band passing of an initial key, the so-called FDSK, which can be conveyed by a QR code. The communication on the bus for conveying the keys is encrypted as well. The second part of the first set of KNX Secure specifications is KNX Net IP Secure. This offers the following features: data integrity. This prevents that a hacker in a KNX installation that uses an IP network, a LAN, can inject manipulated KNX Net IP frames. Freshness. This is the protection against replay attacks. Confidentiality. This prevents that a hacker gains knowledge of what is going on in the building by observing the KNX message traffic. Authentication. This allows that the communication partner are able to trust each other. KNX IP secured server authentication, client authentication, and group authentication, which builds a group of trusted devices. In group authentication, every participant that proves knowledge of the secret backbone key is considered a legal member of the KNX IP routing multicast group. Communication modes. KNX IP secure solutions are foreseen for Unicast, KNX IP device management, and KNX IP tunneling, as well as for multicast, that's KNX IP routing. There are a few services that are needed for KNX IP secure. The service type ranges go from 0950 hexadecimal to 09FF hexadecimal. The first service is the secure wrapper. The original KNX IP frame is encapsulated entirely and is totally encrypted, opposite to data security, which only encrypts the payload. The secure information contains the following. For Unicast, it contains a secure session. The secure information contains the following. For Unicast, it contains a secure session identifier, agreed during the setting up of the secure session, or the value 00 for multicast. It also contains the sequence information to avoid replays. For Unicast, this is a secure Unicast sequence number, and for multicast, this is a timer value. I will explain more about this later. Further, the secure information also contains a KNX serial number of the sender of the wrapper frame, or it contains a message tag 00H for Unicast or an arbitrary value for multicast. This makes that two messages sent shortly after each other can be differentiated and are not seen as a replay attack. The message authentication code is a 128-bit encrypted CBC MAC. Timer notify is a further message. Participants in a KNX IP multicast group share a common synchronized timer. The sender includes its timer value, and the receiver compares this with its own local value. Two old frames will be rejected, but younger frames are accepted, and even make the receiver adjust its local timer value. The default value for this value is 2000 milliseconds, but you can verify this from 400 milliseconds to 800 milliseconds depending on the local IP network. I also want to shortly mention some further extensions to the KNX security field. In 2016, we already approved AN169 secure push button configuration. This allows to add security to the push button configuration and runtime push button motor devices, next to other changes like more efficient linking and starting the link procedure from the actuator. The device linking can either be started with a Diffie-Hellman key agreement mechanism between sensor and actuator, or it has the possibility to be started in the actuator if some FDSK can be read. AN170 Group Object Diagnostics. The use of encryption allows for more causes why a message is not handled by a receiver. For instance, there may be something wrong with the encryption. For instance, a group key or an outdated configuration is wrong or is still used, or a sender and the receiver are out of sync with the sequence number. Additionally, with the encryption, it is no longer possible, e.g. from ETS, to simply send a group message to the device. Therefore, some means were necessary to support the diagnostics of group objects. This is solved through a function property which allows the following. It allows to send a value to a group object. It allows to read a value from a group object. It can command a group object to send its value on the bus, or it can command a group object to read a value from the bus. AN183 IP system broadcast. KNX IP devices can only communicate with each other if they use the same KNX IP multicast address and the same KNX IP secure backbone key. Now there's a use case. Imagine that a new KNX IP device has to be added to an existing installation with existing KNX IP secure devices and an already configured KNX IP router. ETS can only reach that new KNX IP device if it uses KNX IP routing and switches to the default KNX IP system setup multicast address. This can, for instance, not be done from the TP1 side of the KNX IP router. To circumvent this, an IP system broadcast has been introduced. The broadcast is known from KNX radio frequency, for instance. This is supported via the new KNX IP system broadcast frame, which looks like a classic routing frame, only with a dedicated service. Additionally, the R domain address serial number write PDU has been extended to allow for secure transmission of the multicast address, security version, and backbone key. KNX IP Core version 2. That was application note 148. This introduces TCP. As for secure unicast connections, KNX IP tunneling and KNX IP device management, it is important that the packet order is maintained, because packets, remember, with the wrong sequence number will be rejected. Additionally, this application note introduces a new search request extended, which allows limiting the responses to devices in programming mode or the devices with a given MAC address. AN185 KNX IP tunneling version 2. This allows the tunneling client, when setting up a tunneling connection, to indicate a specific individual address that it wants. This is because for data security, the key for point-to-point communication is linked to the individual address. So getting the proper individual address is necessary. Tunneling v1 servers just give a random tunneling slot, out of control of the tunneling client. Also, this application note introduces the new tunneling information div, which contains all tunneling individual addresses and indications whether these could be usable for the client, are free, or whether the client would be authorized to use these slots or not. In order to avoid that the tunneling client has to open a more powerful KNX IP device management connection, the following extensions are additionally foreseen. The extended device info DIB, which includes the medium status, the maximal EPU length, and the device descriptor type 0. Tunneling feature services, as known already from USB. That is additionally to allow reading, reporting, and setting features in the tunneling server, like the manufacturer code and the active EMI type. Now let's come to the second phase of my presentation. The new features. The first new feature that I would like to propose to you is AN 192 coupler security extensions. The goal is to allow for communication between secure devices and plain devices. The use case: allow communication between plain KNX devices and secure KNX devices. The secure devices are a part of the KNX network protected with KNX Secure, e.g. on radio frequency, or an outside TP1 line. The plain devices are on a part of the network that is assumed sufficiently safe, e.g. built in the wall. The solution to this communication challenge is the KNX Security Proxy. The KNX Security Proxy is a coupler extension. This is an extension that can be added to the coupler by the manufacturer. It makes no sense that the plain and the secure communication is on the same subnetwork, so the coupler is the logic place where to do such translation. This can be in the TP1 coupler, the TP1 RF media coupler, or in the KNX IP router. The security proxy works bidirectional. It translates between plain and secure multicast group communication in both directions and transparently. It works only for group communication. Translation of system broadcast communication and point-to-point communication is not foreseen. Functionality. Plain message routing control. The primary condition is always the normal routing according to the filter table of the destination individual address. Additionally, it can be controlled if plain frames back. Group communication only. Yes. Come on. Functionality. Plain message routing control. The primary condition is always the normal routing according to the filter table or the destination individual address. Additionally, it can be controlled if plain frames for unicast, multicast, and broadcast should be routed. Secure proxy for group communication. For each side of the coupler, there is a list of group addresses and encryption keys to translate between plain and secure group communication on that group address in both directions. Obviously, the secure proxy needs to keep track of the sequence number of the secure numbers of the secure devices. So it also has a single common list of individual addresses and their last valid sequence number. This is available for standard group communication as well as for LTE mode property multicast communication. Temporary whitelist. If the routing of plain messages is blocked, then ETSTEL can still open a temporary channel through the coupler. For unicast, this is between a sender and one or more communication partners. Unless retriggered, the coupler automatically closes these channels after 60 seconds. Temporary whitelist and system broadcast. This allows to control whether broadcast and system broadcast can be sent on the primary side and on the secondary side. The current state is that the AN192 copper security extensions is an approved standard. It is tested in the ETS plugfest in this month. Yet there are considerations at the location of the properties, certain functionality like the exception handling, and more, so an update may be expected. A further application note was the application note 193, access policies. The goal is to fix the permissions. A permission is an indication of the access for reading and access for writing. Use case: an access policy defines a service or defines for a service or resource whether it can be read or written in function of the security mode, the role, and the security. An access policy defines for a service or a resource whether it can be read or written in function of the security mode on/off, the role, unlisted role, role X, or the true role, and the security, authentication or authentication and confidentiality. For instance, the programming mode. This can, with disabled security, be read and written by anybody, but with enabled security, it can only be read and written with authentication and confidentiality, and only by ETS. Use case. Okay. So the solution for this has been to fix the access policies for existing and new services and data. There can be two options. Either the access policies are fixed at service level, and this means that already the knowledge of the service lets conclude on the access policy. This is the case for services that only carry one variable, like the APCI domain address right or the APCI individual address right. Or the access policies can be defined at data level, which is the majority of the definitions of the access policies. The access policy in this case depends on the actual data that is being accessed by the service. The typical case is if the service payload has a sub-addressing of the data, like an object type or a property identifier in the property services. The current state, AN193, is an approved standard. Additionally, in new application notes, in new specifications, the access policies are always considered and fixed explicitly. AN194, mastery set of resources. The goal of this application note, or the goal of specifying the mastery set of resources, is to know the guaranteed state of devices after a mastery set. What's the use case? Remove the KNX security information from the device. For instance, keys and communication partners have to be removed and parameters have to be reset so that confidential information is not leaked when a device is removed from an installation. What's the solution? We define the actions that can be taken at the mastery set. The following actions are possible. It can be not influenced. It means that the mastery set does not influence the value of this parameter or this variable. It can be recalculated. It can be set back to a default standard KNX value. It can be set back to a default value which is implementation specific, or the mastery set is not applicable. This is typical for function properties. For each of these actions, it is defined what it may or shall mean for the device and what ETS can do. Fixing the actions for all standard resources for all types of mastery set has been done. Functionality. The goal is to easily and reliably bring the device back in a safe state. This does not need an unload procedure with telegrams on the bus. Simply a mastery set is sent and ETS can assume that all critical data are cleared or have assumed usable values. Current state. AN194 mastery set of resources is an approved standard. Recently, we have approved the application 0203, USB local transport layer for secure devices. The goal? A KNX device with USB connector over which it can be downloaded securely. The KNX data security specification so far focused on fixing the security for the bus communication. Local download via USB with secure telegrams was not possible. Use case: fast download of secure device configuration. The use of data security adds extra data to the download and thus makes it last longer to complete, despite the use of long frames for memory access. Download via USB is faster. The solution? If security mode is enabled, common EMI service for local device management shall be denied. This is because the common EMI services for local device management are very powerful, and they are in a format that does not allow to use KNX data security. So these powerful services cannot be protected and shall therefore be disabled. Yet these can still be used to give access to essential USB properties, like the PID serial number, the max PDU length, the subnet address, the device address, and the domain address, or in the common EMI server object, the medium types, the supported communication modes, and the active communication mode. The functionality? This now allows for a local secure download. If ETS detects that the target address equals the individual address of the local interface, it will, after confirmation by the user, continue the download via the common EMI transport layer over USB. This is at transport layer level and up, so it allows that secure SR data messages are exchanged with the device. The current state: AN203 USB local transport layer service has been accepted in release for voting in September 2020. Outlook to the future. That's the third phase of my conference presentation. First of all, the firmware update. What's the goal? The goal is to allow a firmware update in the installed KNX devices. This can be a small patch, a replacement of a routine, or a complete update of the device's KNX stack, or even other functionality. What's the use case? The first use case would be to allow for the correction of security flows. If it appears that the device has security weaknesses in its code, then firmware update should allow that these get resolved, or an update of the security protocol. If the security protocol is updated, it should be possible to upgrade the stack in the device to support the newer version. This will of course be limited by the memory space available in the device and the kind of changes that are made. Just changing some security parameters or really using a different security algorithm, for instance an alternative to CCM. The solution is a firmware update supported by ETS. This allows that standalone manufacturer-specific apps do not have to be installed, maintained, and used. ETS could know, it can ask, or it can be informed about firmware updates and suggest these to the user. What's the functionality? The overall procedure is as follows. ETS is, as said, informed or gets responded that there is an update for a device, e.g. from the KNX online product catalog or from the manufacturer's website. Of course, this has to be done secure. The firmware updates have to be signed in a way that the device can verify the signature and trust the update. Versioning. The firmware of a device is not a monolithic part, but it can consist of various, even further freely substructured parts. These have to be identified and versioned, so that the ETS and the device can negotiate on which parts need to be updated. Possibly, there can be mutual dependencies between the versioning of the parts. Example, one part cannot be upgraded to version 1.1 if not also another part is at least version 1.1. Such dependencies need to be described in the firmware update that is provided to ETS. Communication modes. The obvious choice for a firmware update, just as for downloading an application program, is point-to-point communication mode, unicast. As there is typically more than one device of the same manufacturer in an installation with the same state of the firmware version, in order to use the bandwidth of the bus efficiently, also multicast is considered. This requires that the devices to be downloaded are found, selected, and other devices are excluded, and also that the procedure for each device is verified individually. What's the procedure now in more detail? Based on the information of the provided firmware descriptions, chunks, blocks, versions, and dependencies, and the information provided by the devices, ETS can conclude on the paths that have to be downloaded. Then happens the actual download. This may use classic extended memory services or another service. This still has to be fixed. And then the final step is the verification. Finally, ETS and the devices have to verify if all paths have arrived correctly. This is done by means of CRCs. If paths are missing, these can be resent in unicast or in multicast, as is most efficient. Then, the firmware has to be activated. If ETS and the device are satisfied with the transfer of the firmware update, then the new version can be activated. The current state? This is still a KSG discussion topic. A lot of aspects have been discussed, but the work is not yet in a consistent state. It's not yet known when this will be voted and when this will be available in ETS and in the devices. Another active topic is the cloud FDSK. The goal is to avoid scanning and managing QR codes for KNX Secure devices. QR codes have to be taken from the box and removed from the devices and scanned. This goes pretty fast, but for large installations with hundreds and thousands of devices, this is still time-consuming. Additionally, these QR codes have to be stored somewhere safe and have to be passed to the legal owner later. The goal is thus to win time, especially installations with hundreds and thousands of devices. Obtaining the QR code could go faster. The use case is thus focusing on these larger installations. The solution: have an online FDSK server. The FDSK is not obtained by scanning a QR code, but by asking it from a cloud server. Every manufacturer can have an own server, or there can even be shared servers. And it is based on the KNX serial number. ETS reads the KNX serial number of the device because this is a unique identifier. It can be obtained by enabling the programming mode in the device. By means of this KNX serial number, ETS will then ask the FDSK from the cloud server. The functionality foresees in a challenge. If there is internet connectivity, the FDSK server will, via ETS, send a challenge to the device. The device has to respond with a cipher of the challenge and protect it with the FDSK, so that the FDSK server can verify that really the intended device with the claimed KNX serial number is installed in the installation. If this proves positive, the FDSK server will provide the FDSK to the ETS. What's the current state? The initial IDs have been analyzed and solutions are proposed. Attack vectors for each solution are considered and measures put in place so that an acceptable security solution level is reached. It is not yet clear when the solution will be completed and provided to voting. When this is done, it can be integrated in the devices and the ETS. This completes my presentation for today. Thank you for your attention. Bye-bye.